welcome to today's colloquium. It's my pleasure to introduce James Ho, our speaker today. He comes from MIT, where he's finishing up his PhD research. He started out his grad career doing a lot of hardware design, including a network interface card for the Arctic network, and turned his attention to actually how do you design hardware, how do you come up with different hardware descriptions. And that's what he's going to talk about today.
Okay, thank you. So I want to talk about operation-centric hardware description and synthesis. This is really a new way to design hardware that will make hardware development much easier. So almost all high-level hardware descriptions are operation-centric. For example, we can look at a microprocessor manual. What a manual tells us is how are the states of a processor updated when we're executing a particular instruction, right? And at a high level, we understand that the behavior of the processor should correspond to some sequential interleaving of these per instruction operations. And furthermore, we also assume that these operations appear atomic. Right? This may not be how we actually implement this processor, but that's really how we think about and interpret these high-level descriptions. So in today's design practice, to produce hardware, a high-level hardware description has to be first translated by an expert designer into a state-centric description. So what I mean by that is some sort of cooperating finite state machines, right? And getting this translation correct is actually very difficult because managing the interaction and synchronization between these finite state machines is just like writing a parallel program. And most of us are not naturally good at thinking about things in parallel. So in the framework that I'll talk about today, we're going to basically bypass all this translation and synthesize directly from an operation-centric description. So in the framework that I'll present, we're going to describe hardware design as term writing systems, or TRS. So TRS is a very well understood formalism that has been used quite extensively to give the operational semantics of programming languages. Informally, a term writing system is made up of a collection of rules. And a rule has a pattern and a predicate condition. And given a term, for example, here we have GCD of 2, 4. If the pattern matches the term and the predicate condition can be satisfied, we say we can apply this rule to rewrite this term according to the right-hand side expression. So applying the rule to this term, we get this new term. Okay? And the rule can also apply to just a part of a term. So given at this point, the only rule that can be applied is this one, rule number 3. And when we apply rule number 3 to just this part of the term, we get the next term. And then rewrite would iterate over and over until we get to a term that we cannot rewrite anymore.
So you said rule 3 is the only one we can apply at that point.
Right.
Rule 1 fails to apply because of type?
So yeah, these we actually, I'm not talking about types right now. We'll introduce type later, but B has to be integer type. That will come up later. And so in our interpretation of term writing system, the effect of a rule is atomic. So what I mean by that is when you apply a rule, you apply the rule completely before the next one can begin. And if in a given state, multiple rules can become enabled at the same time, what the semantics tells us is you can non-deterministically choose any one of the enabled rules, apply it atomically, and then rewrite has to start from scratch on the next step. And what this atomicity is buying us is that when we're looking, formulating a particular operation, a particular rule, we can safely assume that nothing else is going to change the system at the same time behind our back. So some of you may be thinking or wondering, what has this got to do with designing hardware? Well, so that's actually the best part. We have designed hardware. It's so easy, we don't even know about it. So for my thesis, what I've done is I've written a compiler that can take a description in this notation and generate synthesizable Verilog description out of it. And if you have suitable reconfigurable hardware, we can actually test it out and see if it works right now. So let me go into interrupt the talk and go and do a little demo. So let me first show you what the description actually looks like in concrete syntax. So this is in actual syntax, and here are the rules that I showed you, and these are the type declaration for the terms in the system. What's up here is a sort of a wrapper to implement I/O. So when we build a module, we can actually interact with it. And what I can do, yes?
Give us a sense of how many terms or rules you need to implement. What did that, the first line was just a page of rules. What part of hardware does that implement?
What hardware does that implement? Oh, I'm sorry. This guy? Oops, did it come up? Oh, it's already open. Yeah, so these are the same rules as on the presentation.
Oh, sorry.
Right, and I gave the so I included the type definition for the terms.
Sorry.
These are the I/O wrappers, but this is Euclid's algorithm for GCD if you guys haven't figured it out. So I can call my compiler, and so that's how long it takes to generate synthesizable Verilog from that description. And what I have here is a PCM-CIA card with a Vertex 300 FPGA on it. And I can take the output of the compiler, so these are newly generated files. Right, so this generates a Verilog file. I don't think we want to read it. But I can take this Verilog file, send it through Foundation tools, and create a configuration for the FPGA in about 10 minutes. And I did that before I got here. So I have just put in the FPGA, and now I can run a program to download the configuration that was created for the application we just developed onto the FPGA, and now we can send numbers to the hardware and compute the greatest common divisor between two integers in hardware. So we can try out some numbers like 39 and 51, 39 and 52. I think that's right. Right? But what's happening now is the computation is actually being done on the FPGA using what we had just described on the slides. Right? The software is actually only passing number back and forth. There's no cheating going on here. Okay, so let me get back to the talk. Oops, I got to skip through this again. So in the rest of the talk, what I want to do is I want to say a few more words about how to describe architecture, microarchitecture, using this language. And then I'm going to show you how to synthesize hardware from an operation-centric description. And finally, I have one more design that I can show you, and then I'll say a few things about related work and future work. So formally, a term writing system is made out of a collection or a set of terms and a set of rules. And in the context of hardware description, we should think of the terms. We think of terms representing the different states a system can get into. And the rules describe the transition or the operation in a particular state. So if we want to describe an architecture, the first thing we need to do is say, what does the term that represents this microarchitecture look like? And in the language that I developed, we do this with a type definition. So here, we're trying to model a two-stage pipeline processor. At the highest level, this system has three parts: the input port, an output port, and the processor core. So when we define the top level term, it's a triple of three things in it. Right? The processor or the processor core itself is more complicated, so we have to also define, what is a proc? A proc here is defined to have four pieces: program counter, instruction memory, the pipeline stage buffer, and a register file. And then we go on and define what are all the pieces. So I can quickly go over this. A program counter here is defined to be just a 16-bit integer type. An instruction memory is an array of instructions indexed by a program counter type. A FIFO is more interesting. So the pipeline stage buffer is a FIFO of instructions. So in our design abstraction, we're going to use FIFOs that are bounded but with unspecified size. So what this allows us to do is to describe the behavior of this pipeline processor, describe the behavior in the two separate stages independently with the FIFO in the middle of isolation. And only at the very end of synthesis do we instantiate a special FIFO implementation that only has one register in it to get a fully synchronous pipeline implementation out of this. So we're at the register file. Register file is an array of values indexed by the register name. Register name is a union type. What this means is a term of this type can look like any one of these disjuncts. And value is a 16-bit integer, another 16-bit integer type. Input port and output port here are declared to be something like a value, a 16-bit thing. And we have special annotation in the front that tells the compiler to map this part of the processor term into an input port or an output port when we synthesize it to hardware. And finally, we can define the type for the instruction term. So instruction term is also a union type. We have one disjunct for each instruction that we're modeling, and each disjunct has a construction name. It tells us which instruction this is. Right? And by giving this type definition, we sort of have captured the state of this processor. And before I describe the behavior of the processor's rules, I need to say just a few words about the notation we use for array and FIFO. So arrays and FIFOs are built-in abstract data types in our language. And if you see an array A, if you see this A referenced by R, we're simply referring to the R's entry in A. And if you see this notation that says A, where R gets V, we're setting the R's entry of A to V. And FIFO is another abstract data type. It has 4 primitive operations. There's a Q dot first, which allows us to look at the oldest entry in a FIFO. And then we can also change the state of this FIFO by enqueuing a new value, dequeuing the oldest value, and just clear everything out of the FIFO. So with that, we can start talking about behavior. So now I'm going to describe just the operations in the first stage of this processor. So this first rule describes the fetch operation. And what this rule says is that given any processor term, anything that matches this pattern, we can always enqueue the current instruction. From the reference from the instruction memory, we enqueue the current instruction, and at the same time, we should increment the program counter. That's a fetch operation. Right? This rule may look like it can fire forever, but remember, we said the FIFO the size is bounded. We just don't know how big it is. So for any rule that enqueues into a FIFO, the compiler generates this implicit predicate condition that says the FIFO better not be full when this rule wants to fire, or the rule cannot fire when the FIFO is full. And that describes what happens in the fetch operation in the first stage of this processor. Now we can describe what happens in the execute stage of the processor independently. And we can describe the execution of each instruction with a different rule. So this is the rule for the add instruction. So what it says is, if the oldest instruction in the pipeline stage buffer is an add instruction, what we should do is update the destination register with the sum of the arguments, and at the same time, remove the executed instruction. Again, when you try to read something out of the FIFO, this is also an implicit predicate condition. So let's look at something slightly more complicated. So there's an instruction called branch of zero instruction, right? So here, the oldest instruction in the pipeline stage buffer is the branch of zero instruction. And turns out the condition is not zero. So in this case, the instruction is a no-op. And what the rule says, you just throw the instruction away without changing anything else in the system. So what happens if the branch is actually taken? Well, so if the condition is met, then of course, we have to restart the program counter at the correct target, right? But at the same time, we have to clean out the content of the pipeline stage buffer, right? Because we have no guarantee how many instructions the fetch rule has fetched speculatively down on the wrong path, right? So to guarantee starting from a correct state, we want to end up in another valid state, then we must do this. So now notice, right, both the BZ taken rule and the fetch rule, they both modify the program counter field and the pipeline buffer field. Right? But when we're describing each operation, we don't have to worry about race conditions between them. It's because we had this atomic interpretation of these operations. And I can complete the process description by giving more rules for the different instructions. But notice how, what I said about branch and add doesn't depend on what I will say about subtraction or load or store, right? Each operation does not destroy the correctness of already correct operations. There's an easy way to compose behavior as operations. So now we're ready to look at and see how do you get hardware out of this. So for a term writing system to be synthesizable, it has to meet two restrictions. First, the type definition cannot be recursive. And second, a rewrite rule is not allowed to change the type of a term on a rewrite. So if these two conditions can be met, what we know is that given any TRS, we can always represent the terms in the system using a finite set of state primitives like registers, arrays, and FIFOs. And furthermore, what we know is that the rules now are just combinational logics that compute the next state value for these state elements. And when we look at a rule, we should think of a rule as having two parts, right? There's a pi component and a delta component. So pi is a Boolean function that tells us when given a particular state S, is the rule applicable? And if pi evaluates the true, then the delta function tells us what is the new value. And if the pi evaluates the false, of course, the rules are not applicable, and we're not going to change the state of S. And we can map this into circuits. So in a circuit representation, the pi function now is just a Boolean logic that looks at the current state. It generates an enable signal that's asserted whenever the operational rule is applicable, right? And we have the delta component. The delta is also a combinational logic. It looks at the current state and computes the new value when the enable is asserted. And actually, in circuit implementation, delta has to compute how to control the states to receive the new value. And when we're doing this translation, this mapping, because not all rules are going to look at every single piece of state or modify every single piece of state, we can leave out the untouched pieces in this mapping. And we can basically map every single operation independently into the structural representation. In the end, what I have to do now is to combine their effects. And let me explain this by looking at a particular example. So the program counter register, right? So we're using a register with latch enable. The latch enable for the program counter is driven by the logical OR of all the rules that can change it, right? What this means, if any of those rules are enabled, we know a program counter is going to receive some new value. And the actual new value should be selected through this multiplexer controlled by those enable signals. Yeah, there's one thing wrong with this. You're probably going to say it.
Well, I guess I was wondering what, even before, if you leave out conditions, if you haven't specified something, so said no rule applies, does your system detect that?
The simulator will. The system will just stop. I mean, that's the behavior you described, right? We assume that the compiler assumed that's what you wanted, but we can't read your mind, right? But the thing is, if this turns out to be a bug, what you do is you debug your design in a simulator, and the simulation you can see that no rules are enabled becomes enabled at some point, and then you can go back and check to see, are you missing some behavior? Okay? So I was going to point out, the problem with this scheme for merging the effect is that there better be only one pi enabled in a clock cycle. Otherwise, this doesn't work. So let me give you a simple solution first. So to resolve this in the simplest solution, instead of using the pi signal to enable the states directly, we use the set of arbitrated, we call them the phi signals, to enable the states. And here, for the reference implementation, we're going to use just a priority encoder to assert at most one phi whose pi is asserted in a clock cycle. With this scheduling, in effect, what we have created is a correct implementation that executes one rule per clock cycle, right? So the scheduling gives you a correct implementation, but I can't say it's a very good one. Because remember, when I described the pipeline processor with two stages as separate, using separate rules to describe the different operation in different stages. If your implementation only fires one rule per clock cycle, you have a processor that can still execute the program correctly, but it's not a pipeline processor. It's something, but it's not a pipeline. So what my compiler has to do is to go in and find concurrency, find rules that can be executed together and try to maximize hardware concurrency. So we want to try to execute multiple rules per clock cycle. But remember, we can only do it if the concurrent execution produces the same result as the sequential execution, because that's the semantics that the designer assumed, right? So if I give you two rules, and both rules become enabled in some state, what are the conditions that allows us to do this? Well, first, if I apply one rule first, apply the effect to the state, it better not cancel the applicability of the other rule, and vice versa. Otherwise, there is no legal sequential execution of those rules, right? And we also want to make sure the order of application doesn't affect the outcome. And as an extra implementation consideration, we're going to require that the result of the sequential execution can be reconstructed from applying the effect of those two rules directly onto S, onto the state directly. Right? Otherwise, this composition may imply some sort of cascading combinational logic, which is not always good. And we say if two rules can satisfy these conditions, we say those two rules are conflict-free. And now we can prove a theorem that says in any given clock cycle, you're allowed to fire multiple rules and still get a right answer as long as all those rules are pairwise conflict-free. And we can take advantage of this theorem in a more aggressive scheduler. So to build a scheduler for this scheduling, we have to first analyze the conflict-free relationship between all pairs of rules. And to compute the conflict-free relationship is actually very expensive. So in my compiler, we substitute in several rounds of more conservative tests. But in any case, once we have found as many conflict-free relationships as possible, we can then try to partition all the rules into maximum number of non-overlapping sets, such that if two rules belongs in different sets, we know they're conflict-free. And once you've done this partitioning, we can now schedule each set independently by itself, right? Because whatever we schedule for one set, whatever it selects will be conflict-free with the selection made by all the other sets. That's guaranteed by this partitioning algorithm. Right? And now the scheduler can actually enable select multiple rules to fire in the same clock cycle, but we don't have to change the state update logic I presented earlier. Because this scheduler will also guarantee that even though multiple rules fire in the same clock cycle, but at most one rule will touch a particular piece of state. So this scheduler is going to allow you to fire more rules per clock cycle. And it's also going to reduce the clock cycle time, right? Because once you have done this partitioning, we replace this sort of monolithic giant scheduler, single scheduler, into multiple smaller schedulers that runs concurrently. And these smaller priority encoders are actually smaller and faster. And another thing is, once we've done the partitioning, rules that are not related, the pies and fees, they don't need to be routed to a central location of arbitration anymore. They can be arbitrated locally. And this leads to potentially faster cycle time. Yes?
So the partitioning is not static.
Yes.
Is there anything that we need to manage to dynamic partitioning?
Meaning, what do you mean?
Well, now the sets are checked
Right.
at runtime, right, but independently. But it seems like there might be some cases where there are overlapping sets that you might be able to get some advantage by checking it.
I'm not sure what you mean by checking it dynamically. I'm not sure what you mean by checking it dynamically.
Because you have to make some choice in terms of the partition.
Not in this case. This is actually there's no choice. It turns into a connected component problem. There are more aggressive scheduling where choice comes into play, but the one I'm presenting now, there's no choice. So the synthesis algorithm and the language, yes, Professor Anderson. Well, you were actually there when I was undergrad, so.
Those are Tom. Maybe I got lost in the grocery store, but if I was trying to design this hardware without this tool, and as a consequence, I had built this kind of state machine model into my hardware.
Right.
And it would seem like what I would do is build some set of kind of logic that would transition my current state into my next state, that would embed much of the rules that you have.
Right, but the thing is, when you design, the way you design, the traditional way of designing hardware is design them as pieces, these finite state machine pieces, and you specify each state machine separately. And if two state machine needs to coordinate somehow, the way to do it is by designing it right. You look at it very carefully, make sure when one machine is presenting a signal, the other guy is ready to catch it. But imagine a year later, when you come back to change one machine, how many other machines do you need to change?
Okay.
Right? We're really specifying things in a sort of orthogonal to that view.
So that's the case, that would be the case, for example, where multiple, if I had multiple state machines and each of them was doing some operation in parallel, then that would be the kind of parallel case where I could apply rules in each.
No. So the way to think about it is each rule is specifying a little bit of some finite state machine, right? So this is a way to describe multiple finite machine. Each rule is describing like sort of something that can happen in a particular instance in time, right? Things that you require to happen atomically. We can talk about this later.
Yeah, I'm just trying to understand really the difference between what someone would do in practice today versus how that looks different to the programmer or the hardware designer versus the two. And I think you've answered that, so that's fine.
Yeah, so I think the easiest way to think about that is designing hardware today is really like writing a parallel program. Here, we're giving you a different representation that actually has a sequential interpretation, but it has implicit parallelism that a compiler can find. So I think that's the best way to think about it. All right, so the kind of things I've been talking about in this presentation has been implemented in a compiler called TRAC. It's the term rewriting architectural compiler. And the TRAC takes in a design specification in TRS and produces synthesizable Verilog description that can be compiled by commercial tools to target a number of different implementation technologies, including FPGAs. And the compiler can also generate simulatable descriptions to help debugging. So one of the designs that we have looked at is this 5-stage pipeline on MIPS R2000 processor. And to get a feeling for how good are the RTLs that we're generating, one of the colleagues in my lab has implemented the same microarchitecture using standard design practice in Verilog RTL. And when we send both the descriptions through the synopsis, we have to compile my description first by TRAC. And once I've done that, when we send both RTL through synopsis for these two gate array libraries, you can see the results are nearly identical. Right? But the difference is, a description in this term writing system, I can do it pretty quickly in about a day or two. Whereas the Verilog version took almost 5 days before you can fully debug it. I mean, it's not the complexity in writing down. The description is not very large or complicated. What's hard about the old way of designing things is how do you make sure all the interaction in different pieces are happening at the right time? Right? Scheduling of managing of concurrency is what's hard about the traditional style description. And another thing is, we really shouldn't be too surprised these numbers are coming out nearly identical. Because remember, after all, we're describing the same processor, the same microarchitecture, and we just happen to use very different methodology. One's faster, one's slower. So what I'll do now is I'll do another demo. So what I have here so I have the source description for the MIPS processor. And again, we begin with a type definition of the processor term. And here, I don't know how well you can see this, but this is the definition for the processor. There's a program counter, a register file, several pipeline stage buffers, input port and output port to access instruction and data memory. And we can go ahead and define the register names. And oops, where am I? And here we're defining the ISA. And once we had captured the state, described the state of the processor, we can describe the behavior or the operations in different pipeline stages. Different operations for different pipeline stages, different operations for, here in the decode stage, we use different rules to describe the decoding of different instruction types in the MIPS ISA. And again, we can also take a description like this and just run it through my compiler. So this is a larger design, but it shouldn't take much longer. Right? So what the compiler actually does is it generates two versions of the same of the same design. First, we generate a straightforward version, and then in the second path, we go in to do a more optimized scheduling. My computer's running extra slow today. But scheduling is hard. Maybe, oh, because it's running in the background. Okay, sorry. So you can see the Verilog files being generated. So what's happening here, what's happening there was my compiler actually does its own RTL optimizations, right? So Synopsys does a pretty good job in doing RTL optimization. The reason my compiler does its own optimizations in RTL is that my compiler has access to the source code, right? I have access to high-level semantics embedded in the source description. So a lot of times I can figure out things easier or faster than if Synopsys, compared to Synopsys working on just RTL. For example, if you have two signals and they come from two conflicting rules, I know they will be mutually exclusive because my scheduling guarantees that. It will be very hard for Synopsys to infer the same kind of implementation by looking just at the RTL. So now I have generated the synthesizable Verilog. Again, I can download the configuration onto the FPGA. So this larger design will take about half an hour on the foundation, in the foundation tool. But what's happening now is I downloaded the configuration for the MIPS processor onto the FPGA. And we're going to use the FPGA as an emulator now, right? What has also been downloaded is the actual MIPS binary for the Fibonacci program. And now we can run the FIB program on the emulated processor. Oops. Let me try that again. Type too fast. 1, 2, 3, 4. Okay. Right. But now the computation is being done on the emulated MIPS processor. So let me show you what that looks like in my next slide. Right. So imagine this could be a very powerful architectural study tool. Right. If the architect has some idea in his head about some microarchitecture mechanism, he can capture it in a very concise manner. And if he cares, he can generate working prototypes very quickly. Yes?
So it seems like what you've sort of done is you've taken some of the errors that you might get in trying to specify process communication in pipeline stages, for example. And you've hidden that into the rules, but now I've got the problem of rules that may be incorrect and may be, for example, I might have two rules that can fire in the same condition.
Right. And do you mean for them to fire in the same condition?
Right. And I don't mean them to. I have an error there.
So you made a mistake. Right. So there are two kinds of mistake, right? One is for this more naive mistake, right? Each rule should guarantee the invariant. If I give you a correct starting state and you're enabled, you should produce you should produce another valid state. Right there, I can't help you because you're given the spec, you should get that right. So the more subtle mistake you can make, once you have to guarantee every rule satisfies the invariant, is that you can have sort of, I think what you're getting to is sort of unintended non-determinism.
Right.
You didn't mean for it to happen, but you wrote something down, and then you might get into lifelock and things like that. So I think the last question was about what if you were missing some rules. But these were sort of related kind of questions. But,
for example, I know you can apply model checking, for example, to
right.
RTL descriptions and ask questions about whether you're going to satisfy certain invariants.
Right.
Can you do the same thing in this world?
You should be able to because we're generating RTL. And the thing is, that actually the way we're debugging that kind of problem right now is actually by running the simulatable description, right? And when you get to the simulator, so when the simulator, if two rules are enabled in the same class cycle, the simulator has the ability to halt the simulation and tell you, do you want to double check this? Do you mean this? Right. And there it will help you catch, sort of unintended non-determinism errors. And in terms of formal verification, yeah, you definitely should be able to do it in the back end under RTL. And another form of formal verification that we're doing is actually doing it on the front end, right? So I can give you a description of the ISA itself, and then I can give you this sort of pipeline description of the same ISA. And there are techniques where you're basically trying to simulate one term writing system with another one and do a mutual simulation to make sure one doesn't do more or less than the other one. So we can do formal verification both at the source and at the RTL. I think your hand was up first. Yeah.
If you were trying to build the R10,000 rather than the R2000, would any of the issues, sure there are more rules and so forth, but do any of the basic issues change as you go to a much more complex hardware that is much more in parallel, and both with respect to constructing the rules and with respect to compiling them?
The basic issue doesn't change, right? We're still doing decomposition into operation. I think one misconception a lot of people get is that there's some magic in this, right? There is no magic in this. If you want to implement a processor with branch prediction, with speculation, you have to describe those mechanisms in my language, right? The compiler only knows how to synthesize what you have described. It's not going to suddenly invent mechanism to fill in things, right? But so I have a description of a superscalar processor with branch prediction and speculation, and it's really the same kind of fundamental issues. The new issues you get into are sort of engineering issues. You now have a larger design. You have to break things into modules, right? You do more modular design methodology. Yes.
So kind of an analogy here is that what you've done is parallelism and compiling. And
Yes.
the trade-off always in that space is how do you decide what granularity you parallelize versus what granularity not? What granularity is too fine-grained to really benefit you. So you haven't really talked about the algorithms by which you decide when to break things out into parallel, when to actually implement things in terms of parallel finite machines versus from your sequential.
Right. Well, so the good thing about mapping parallel things to hardware is that there's nothing too fine-grained, right? And what the compiler does, so you give me a operation-centric description. It has, actually because it's non-deterministic, it actually allows a collection of different possible behaviors. What my compiler does is it creates a particular determinist implementation that has the allowed behavior. And so in my implementation of the compiler, I've taken the position that I'm going to map each operation into state transition that can happen in one clock cycle. So that's what I try to answer your question. And I also try to maximize concurrency. Those are set policies.
So you preset the clock cycle first.
No, we map and then we synthesize. Right now, we don't try to meet a particular timing budget. I mean, we're now looking at sort of more advanced methodology where you can actually, because to change the timing, you have to go in and spread a rule over multiple clock cycles. And there are more complicated transformations you have to do. And we're looking at that right now. But my compiler doesn't do that. My compiler just does a straightforward mapping. I think his hand came up first.
I have a question about what stuff you should put explicitly in the TRS program and what stuff should be implicit.
What do you mean by?
The interesting about what's going on here is that you're making the concurrency implicit in how the compiler does things. But there are other issues in how the architecture is designed that are explicit. So for example, you have an explicit FIFO queue for instructions as a buffer between two different parts of your machine.
Right.
If I'm designing the machine, I think I'm thinking about what things happen concurrently and where buffers go and lots of other stuff I don't really understand because of my architecture.
Right.
And I don't know which ones I should make explicit in my program and which ones should be done automatically by your tool.
Okay, so if you're a software person, everything's implicit. You write a TRS, it's describing some computation. The compiler happens to produce hardware for you. Okay, but if you're trying to use the tool as a microarchitect like I am, then what becomes explicit are things like state. All the states are, by giving the type of definition, you're in effect making the state explicit. What else is explicit is atomic events, right? Things that needs to happen at the same time. You're just saying these things should happen at the same time, right? And other than that, what you're really trying to capture are just operations, inherent operation to a particular design.
So for example, you have to decide in advance if you wanted a 10-stage pipeline for 10,000 as opposed to a 9-stage.
Right, but the thing is,
you'd have to write out the rules and then decide, in fact, that actually wasn't a good mapping and then change.
right. But it's not completely bad because if we do this in TRS, right, we're using this high-level notation that has a formal basis to it. I mean, we're now looking at sort of formal, transformations that will allow you to tell the compiler to put add a pipeline stage here, and we can do the transformation on a term writing system for you, and we'll make sure, the two systems will have the same behavior. So there are things you can do. So my tool gives you an easier way to describe pipelines, and if you don't get what you want today, you can go in and change it by hand pretty easily, and maybe next year we'll be able to do it automatically. So let me just quickly wrap up. First, so when you talk to people about high-level synthesis or behavioral synthesis, what people typically mean is describing concurrent hardware as multiple threads of computation. And so this is a big improvement over your concurrent cooperating finite state machine model, because you now have you have a coarser grain granularity for synchronization and interaction. But again, you still need to manage the concurrency explicitly, right? And today, we have commercially compilers for behavioral Verilog, behavioral VHDL. Actually, the hottest thing on the streets nowadays are these two competing languages, System C and Superlog. And there's several research systems, SRL and Spec C. These are all based on multi-threaded abstractions. And in this next category, the project are trying to compile software programs, parallel and sequential, onto a hardware implementation. So in the raw project, they're taking sequential C or Fortran program, automatically parallelizing it, and then mapping it onto a reconfigurable array. And of course, in the Rapid C project, they're looking at nested loops and mapping it onto a pipeline implementation. And so in the DPC project, they're taking a data parallel C program to map into a linear reconfigurable array. And then you have this next category where people are leveraging the familiar syntax of C or C++, but they're also reassigning sort of RTL specific semantics to those constructs. And so then essentially they're describing RTL with a high level syntax. And the difference between this category and that category is that typically you take a description in this category, compile it using the software compiler, you don't end up with a meaningful program. And then finally, there are other languages based on well-known formalisms. So, and these languages tend to be used to describe hardware for the purpose of verification. And as far as we know, no one else has tried to synthesize hardware from high-level formalisms. And finally, let me just say a few words about what we're now trying to do is to find applications for this technology. So one of the things that we're trying to do now is to move on to sort of the more complicated industrial strength microprocessors. We're looking at things like x86 and the Pentium processor. And that's a very interesting project that we're working on is to synthesize hardware cache coherence engines out of cache coherence protocols that are specified in term writing systems and formally verified in term writing systems. And I mentioned this a little bit. This is actually a PhD thesis that's just getting started. He's going to look into how do you take advantage of the term writing system formalism to automatically use transformation to insert pipelining and to resolve structure hazards. Thank you.